All right, well, welcome to this week's colloquium. I'm very happy to introduce our speaker for this talk today is Dr. Mark Phillips. He's a research professor here at the College of Optical Sciences. And his research interests are in developing new techniques and instrumentation for laser-based spectroscopy. Some of that he'll be telling us a little bit about today. I've known Mark for a while, and we've collaborated quite a bit in recent years. And so we're really excited to have him give this talk, and also he is now a full-time research professor here at the University of Arizona, so it's great to have him around a bit more and not only collaborating with us, but I'm sure he's interested in meeting a lot of you as well and forming new collaborations. So Mark got his PhD in physics in 2002 at the University of Oregon. They also have another nice optics program there as well. And then he went on to do a postdoc at Sandia National Labs. That was from 2002 to 2005. After that, he went and worked at Pacific Northwest National Lab, DOE lab, and he was there for quite a while, and that's when I met him. So that was from 2005 to 2018. And he developed a lot of nice systems and instrumentation for a lot of different experiments, but in particular, these external cavity quantum cascade lasers, and he'll be telling us a little bit about some of those applications in this talk. He went on from there from 2019 to 2024. He was a chief scientist at a local startup company, leading a development of commercialization of some of these laser instrumentation techniques. He was also part-time here at the College of Optical Sciences, but now he's full-time, and he's here to tell us about this exciting measurements with explosions and flames, and maybe we'll have a demo, I don't know. And he's also a fellow of Optica that was just awarded last year, so it's great to have you, Mark, and take it away.
Great. Thank you very much, Jason, for the introduction. Thank you for the invitation to speak here. Very excited to tell you about this work. I know if I put explosions in a title, we'll get a good turnout. As one of the students told me this morning, the joke's on you. It's really a spectroscopy talk, but we will cover explosions. I guarantee that. So I always like to do my acknowledgments at the beginning so I don't forget and make sure that I can really acknowledge all of the people that contribute to this work. You'll see a lot of experiments were done in collaboration with Nick Glumac at the University of Illinois, Urbana-Champaign, UIUC. He has a wonderful facility out there for some of these extreme environment experiments, both flames, and he's one of the few university researchers in the country who's certified to work with high explosives and do those experiments in his laboratory. So really unique facilities, and I've been very fortunate to be able to work with him. Also very fortunate to work with an excellent group of modelers at Craft Tech, Combustion Research and Flow Technology. They're out in Pennsylvania. What you rapidly learn if you're working in combustion or high temperature chemistry type research areas is you really need a good modeler on board. These systems are extremely complex, and having that model to compare against and to baseline and interpret your measurements is really critical. So definitely acknowledge their contributions to this work. And then, as Jason mentioned, I spent a number of years at Pacific Northwest National Lab. Still have ongoing collaborations with Hari there. Bruce Bernanke recently retired. Too many other people to list over the years who have helped contribute to this work. And then, again, a long list of funding. Here's some of the more recent funding sources for this work. And then I have to give the obligatory disclaimer about government work. Please don't read it, but it's there. So to motivate this, really the question we're going to ask and hopefully answer by the end of this talk is, how can we measure molecular chemistry and dynamics in extreme environments? So what might that look like? So one example would be if we have a chemical plume being released out into the environment. You can see this is an image. I'll come back to this and give a few more details about how this was made. Uh-oh. But there's a chemical plume being released from up here, and this is imaging, and the color gives you the concentration of the plume as a function of time. So some things we might want to know about that. What chemicals are there? Are they hazardous chemicals? And if so, what are the concentrations? Is it hazardous? Do I need to run away? On a more scientific level, how does the plume propagate through this very complex terrain? You can see all the structure in there and different paths that this plume can take. How can we better understand that? Can we model it? And then, of course, can we measure it from far away? Not sure why that keeps blanking out. Maybe it's just when the movie resets. So another example, I'll talk about this in more detail, and that's methane flares. So a lot of times the industry will burn excess methane in a flare, and we want to know things like how much methane is consumed, how efficient is this process, how much carbon monoxide is generated, for example. Can we measure this without touching it? It's hard to put a flame in a bottle and study it. So we'd like to study it in situ, as we would say. How do chemicals and temperatures vary throughout the flame? You can see there's a lot of structure, varies with time. Let's see if I can play it again. Right, a lot going on there on very fast time scales. And then again, other science questions. How does the efficiency change if we say put a fan and blow winds on it, simulating what would happen in sort of an outdoor facility subject to changing weather conditions? Another example is related to that, biomass burning, so forest fires or controlled burns. This is a very complicated and interesting chemical system. There's a lot of different materials that can burn. Basically an indoor brush fire that we were studying in this case. What chemicals are produced, not only from the flaming combustion, but pyrolysis. As the temperatures rise not high enough to combust, we get other species that are emitted. How many of those can we characterize? How much of them are emitted? How do conditions change again? And how does chemistry depend on local temperature or local conditions? So another one, I told you there'd be explosions. Here's the first one. We'll come back to it. So in a high explosive detonation, what gases are produced? How much of those gases are produced? This can be important for situations, not just military application, but say for mining application. If there's a high explosive detonation for mining purposes, they need to know how much carbon dioxide, how much carbon monoxide is released, and how it will propagate downwind. And of course, for explosions, we very, very much need to know how can we characterize this from far, far away. So in order to do these things, there's a list of things I put together, needs that are absolutely essential, and some of them are desirable, maybe not completely essential. We'd like to get multi-chemicals. As one person told me one time, if you're not measuring at least 2 chemicals, you're not really studying chemistry. It needs to be high speed, dynamic events. A lot of this chemistry is driven by the high temperature conditions, so we need to have a good grasp on measuring that temperature. Quantifying the chemicals can be very important for benchmarking these models that are being developed. Mentioned standoff capability, and spatial resolution is nice to have. That's one of those, I think I put it in the want category. But we do need to be able to resolve what's happening at different points in space in a flaming or combustion type system. So how can we measure molecular chemistry and dynamics in extreme environments? Tunable infrared lasers, that's what I'll talk about today. The asterisk is here because not any tunable infrared laser will do. I'll tell you about the specific needs and the solution that I've come up with to solve these challenging measurements. So I'll start with a brief introduction on molecular sensing and infrared spectroscopy. I'll tell about my solution, the swept-wavelength external cavity quantum cascade laser, and then focus on 3 main application areas. One's a defense-related in chemical weapon agent defeat by high temperature conditions and explosive fireballs. I'll talk about a climate change relevant application, looking at the efficiency of methane flares. And then I'll talk more generally about remote sensing and standoff plume detection. So infrared spectroscopy, very, very general introduction here. Why do we care about the infrared? It's because nearly every gas phase chemical or molecular species has a unique infrared spectral, what we call a fingerprint. So if we can measure the spectrum, that identifies that molecule for the most part uniquely. So if we measure enough of the spectrum, we can tell what it is. Here's a few examples. So a simple small diatomic molecule like carbon monoxide has a spectrum that looks like this in the mid-infrared. You can see it's got these discrete lines, well-defined spacing, regular pattern. This pattern and the position of those lines is the fingerprint for that chemical. Larger molecules, something like a Freon molecule, Freon 134A, this is probably what's in your car air conditioner compressor. Looks like this, so we don't see the lines anymore. They're still there. There's just so many of them, and they're so closely spaced that we can't resolve them anymore. But we can still look at the pattern and the structure and the position of these features, and that, again, is a unique spectral fingerprint for this molecular species. And this goes all the way from simple molecules, complex molecules, to solids or liquids, condensed phase materials. Many of those have distinct infrared signatures that can be used for identification. I'll talk about two main spectral regions. The first one will be the mid-wave infrared, which is 3 to 5 microns, 3,000 to 5,000 nanometers. This is useful for sensing combustion gases, things like CO, CO2, water vapor, nitrogen compounds. I'll also talk about the long-wave infrared. That's roughly defined as 8 to 14 microns in wavelength. This is useful for sensing a very wide range of trace gases, VOCs. Almost everything has some absorption here in the long-wave infrared that we can use for fingerprinting. I like to think of spectroscopy in this way. There's sort of three goals we have for spectroscopy. The first is detecting something. Is there enough of a signal? Do we do our measurement right? Can we detect it if it's there? Second, we want to be able to identify it. Can we measure enough of the spectrum that we can positively identify it and distinguish it from any other chemicals? And then quantify is the hardest one. But if we've done our job right, if we do a good measurement and we do the spectral analysis correctly, the strength of the absorption that we measure is proportional to the number density of the molecule. So we can really get quantification. And when we do all these things, we had a very powerful combination for quantitative spectroscopy. The laser pointer's dying, so I'm going to try to conserve as much as I can. In terms of the science for infrared spectroscopy, what are we actually measuring? It's vibrations and rotations of molecules. They can also have electronic transitions. Those tend to be in the visible. We're focusing on these infrared transitions between vibrational levels and then rotational coupling to those vibrational levels. So the simple model we use for this, you can think of it as masses on springs. So it's, again, a simple diatomic like carbon monoxide. This can vibrate, this can rotate. And if you look at the energy levels that are generated and the transitions between those levels, you can get structures that look, like this, well-defined frequencies in a regular pattern defined by the rotational structure in this case. Again, larger molecules, I'll talk later about DIMP, diisopropyl methylphosphonate, which is a simulant we use for chemical weapons. Larger structure, it still has these same modes. There's just so many of them and they're so close together that they really can't be resolved. But again, the envelope is still very distinctive of that molecule and we can use it to measure it and detect it. Is this one going to work better? Oh, is this a little more powerful? Oh, I like that one. Thank you. I'll try not to. So another very useful feature about infrared spectroscopy, I'm not going to talk too much about it today, but if you remember from your masses on springs and harmonic oscillators, if you change the mass of one of these species, you change the vibrational frequencies, and you can change the rotational frequencies as well. What that means is if we have a molecule like ammonia, and we change out one of our nitrogen 14s for a nitrogen 15 isotope and measure the spectrum, we get a nice shift in the spectrum, and so it really looks like a different molecule entirely, just by substituting one of those atoms for a different isotope. So again, I won't talk too much about that, but that's a very powerful capability of infrared spectroscopy that we use in other contexts quite often. So briefly, I don't think I have to spend too much time on absorption spectroscopy, but just to cover it, we typically use a Beer-Lambert law type relationship. We send light into a sample, we measure what comes out. The ratio of those two has an exponential dependence on a quantity known as the absorbance. So the absorbance depends on the frequency, wavelength. I'm going to interchange between wavelength, frequency, and wave number. They all mean the same thing, just different units for different people. But basically, that's the spectral parameter. It may depend on pressure, depends on temperature as well. And we can express that as a product of three terms, what's known as the molecular cross-section. This is everything about the molecule. The number or number density of molecules, so how many molecules there are along our path, and then the length of the path as well. And so this quantity together, this n times an L, is referred to as the column density. And so you'll hear me talk about either NL or column density as well. If we can define the length, we can get a concentration. Sometimes when we're doing an open path measurement, we don't exactly know the length of the plume that we're measuring, and so we keep things in units of column density. Anyways, this just shows a simple example if we're measuring through a gas cell and we scan a laser. This is what goes in at the top. What comes out might be some absorption, reduced light where it's absorbed. We convert that to absorbance, and this pattern may be representative of that molecule. And the strength, the height of these peaks is related to the number density or column density. So different ways to do infrared spectroscopy. Briefly talk about broadband or incoherent methods. This would be using primarily FTIR spectroscopy these days. It's a very powerful technique. And one of its big benefits is you can get a very, very broad spectral coverage. I'll show an example on the next slide. So you can get a large chunk of the infrared spectrum. This is great for multi-species molecular detection. You can sense any molecule you want to somewhere in that spectrum. But there's some trade-offs. Because it's an incoherent source, it has a low brightness. And so we almost always have to make a decision. Do we want high spectral resolution to be able to see those fine features? Or do we want to go fast? It's very rare that we can do both at the same time. In contrast, we know lasers are very high bright, high spectral radiant sources. And so using a technique called tunable diode laser absorption spectroscopy, we can get a very, very high spectral resolution. We can get very high speed measurement, faster than kilohertz rates, very high source brightness. But with TDLAS, the sacrifice we make is we can't tune them very far. We can usually only measure one spectral line at a time, maybe a few features. And what that means is for multi-species chemistry, we need a lot of different lasers, one for each species that we're trying to measure. And that becomes impractical a lot of times. That said, it's a very powerful, very sensitive technique. It's used in combustion all the time. So the example from a broadband infrared spectroscopy I wanted to put up here is this is an example of an FTIR spectrum measuring gases that are emitted from a biomass burning flame. And you can see all the different spectral features in here. A lot of them are labeled. Lots of chemicals. This is really the strength of FTIR. It's just the broad coverage lets us see so many different molecules. It's slow though. And when you're trying to measure bright sources, you run into a problem that the brightness you're trying to use, your infrared source, may be about the same brightness as the thing that's emitting or the flame, and you really can't distinguish them at some level. And so it doesn't really work that well for combustion type systems. There's some exceptions, but for the most part, it's very difficult to use these incoherent methods for combustion. TDLAS, just to give you an idea of how it works for those who have not done it before or aren't familiar with it. Pretty simple technique. You apply a current ramp to the laser, change the current. That causes thermal heating or index changes, and that shifts the wavelength. And then you measure a signal versus time usually, and then by doing some calibration steps using etalons or reference cells, you can get out what the absolute wavelength is and identify your lines, calculate absorbance spectra shown down here. You can do a spectral fit, and you can extract out number densities, column densities, and temperatures very, very accurately, very fast. Because you're just tuning an electronic signal, the current, you can do it at kilohertz rates or faster, so a millisecond per scan. Much faster as possible, but you do have this limited tuning range. And what makes things worse is the faster you scan, the smaller the tuning range usually gets. So it has been used for combustion, as I mentioned, very powerful, but limited in this tuning range. So can we make a tunable laser that has the broad spectral range of an incoherent broadband source and the high resolution and fast tuning of a tunable diode laser system? And the answer is yes. That's what I'll talk about with the swept external cavity QCL. So I'll talk about that now. So the engine behind this, the light source that we're using is like a diode laser, but it's called a quantum cascade laser. Similar, but some key differences. This year is its 30th year birthday or anniversary. It was first demonstrated in 1994 by Federico Capasso at Bell Labs at the time. Really an amazing marvel of semiconductor design, engineering, fabrication, growth, incredibly complicated structures. I cannot possibly do them justice and talk about all of their wonderful features, but I'll focus on two. They have a very broad gain bandwidth. They can emit large portions of the infrared from each device, and they're tunable. We can move that wavelength around to cover nearly all of the infrared and large chunks of the terahertz as well. What this means at the end of the day for me is it's a great source for IR spectroscopy and sensing. So by itself, these diode sources, these quantum cascade lasers, they emit a large range of frequencies or wavelengths at the same time. To do spectroscopy, we need to control that. And the way I do it is with an external cavity design. If you're familiar with external cavity diode lasers, the external cavity quantum cascade laser is very similar. We've just swapped out our diode laser for a quantum cascade laser. It's a standard Lippmann-Metcalf external cavity design. We use a diffraction grating to select out the wavelength, and then a turning mirror right here. And the angle of this mirror defines a particular wavelength that's fed back into the cavity, and it lasers on that mode. And then we pick off the output off, say, a 0th order reflection off the grating. And so what we can do is we can make our nice narrow band, single frequency laser. And then by changing the angle of this mirror, we can move that around in the infrared over large ranges. And because we can use something like a galvanometer scan mirror, we can do that very, very fast. And so that's really what this comes down to, is taking that infrared source and making it, instead of tuning over a narrow range like a tunable diode laser, we stretch that out from a few wave numbers out to a few hundred wave numbers. So we can now see multi-lines, multi-chemical species, and still do that fast enough that we can capture these fast transient events like combustion type systems. So here's a few of the features. I won't talk about all the details. I do like to point out, though, that if we calculate out what our actual scan rate is, our instantaneous scan rate, it works out to be about 1 million nanometers per second, which is really fast because it's covering such a large range. That's going at about 1 kilohertz, so a millisecond per scan over that big of a range. When you work out the numbers, that's about what you can do with a tunable diode laser system, too. So it's somewhat amazing that a mechanical tuning method can get the same sort of tuning rates as an electrical method. Of course, there's exceptions and interesting ways to get around these, but in general, it works out that way. In terms of the history, so I've been working on QCLs for about almost 20 years of their 30 years history, which is starting to make me feel a little bit old. But I did start working on this back when there was very, very little technology out there around it. So infrared optics were just hard to get that were suitable to use in these lasers. So I spent a lot of time building up this laser technology, using it for a lot of really, really cool applications. I won't talk about all of these, just a few of them. And I've sort of continued that to this day. One of my current pushes is finding new interesting applications, like what I'll talk about later on. And then also looking at commercialization efforts. How can we get this to more people so they can use it in their research? I also like to point out that, I'll be showing some more mature systems today. Back at the beginning, it started like just about every optical laser system starts on a breadboard with mirror mounts from Thorlabs, Newport, big actuators, slow tuning. It's got to start somewhere. But based on this, we've built a large number of other more integrated systems. Every design iteration, it gets better and better and better, slicker and better packaging. So here's some recent laser systems, laser heads and electronics control packages, and a standoff detection system that I'll come back to at the very end. So moving to the next part, I have these lasers, happy to travel. So I've been very, very fortunate working with people all over the country to take these lasers to their labs, do really cool experiments using their expertise in high explosions, biomass burning, flames, flares, all of these things, making some unique measurements and then analyzing the results. So I'll move into that next. I had a little more background here. I think I'm going to skip it. It's a very sort of complicated way and long-winded way to say something that's actually pretty simple. So if you want to measure something that's changing fast, you have to measure it fast. So if we can measure it before it changes enough, we can essentially freeze it, take a snapshot. Think of like a strobe light. If you can freeze it in time, then you can characterize it, and we can take sequential strobes of that. And so really what it comes down to is, can we scan our laser fast enough that we can freeze it, whatever we're looking at, and so it's roughly stable. Then we can analyze it, and we can do that again and again and again and again. The timescales that we'll look at for atmospheric propagation, the turbulence timescales ending up being about on the few hundred hertz timescales, and we can scan that fast pretty easily with these systems. Combustion systems are more getting into the kilohertz, hundreds of hertz to kilohertz rates. Explosions are even faster, but you'll see even at a kilohertz rate, there's a lot that we can pick out from these systems. We'll come back to that. And so if anyone's interested in more of the details, the science behind it, the measurement science and technology, let me know. We can come back to that at the end if there's time. I want to talk about the application areas because I think that's a really interesting part of this work and shows sort of some relevance of this research and how it can solve some interesting problems. So the first one I'll talk about is chemical warfare agent defeat problem. And so the sort of the prototype problem that we're looking at here, and this is work that we're doing for the Defense Threat Reduction Agency under a multi-university consortium called MC Material Science in Extreme Environments. And one of the problems that they've posed is, suppose that there's a chemical weapons storage facility somewhere, and the military would like to destroy that chemical weapons stockpile. And they're going to do that by dropping a bomb or a missile or something like that into this facility. So what they need to know before they do that is that they have an extremely high confidence that they're actually going to destroy that chemical weapon and not partially destroy it or not destroy it at all, rupture all of these chambers and release it into the atmosphere. That would be catastrophic. So as part of the MC program, we're doing laboratory research on simulants. We're not working with live agents. We're working on chemical simulants that have some similar chemical properties to these chemical weapons agents. And we're studying really the science behind this. How efficiently can these materials be destroyed at high temperatures in fireball or explosive conditions? What temperatures does it take to do that? There's people working on additives. Can additional chemical additives be added to the explosions to help neutralize these materials? And really what it comes down to for us is studying multi-species chemical kinetics at high temperatures. And the goal really is developing and validating models that can be used eventually way down the road to predict the outcome of a situation like this, which hopefully would never need to happen. But if it does, have some confidence that it would be done in the right way. So what am I doing on that research area? So we're looking at this chemical weapons agent simulant. I mentioned it before, DIMP, diisopropyl methylphosphonate. Here's its chemical formula and its structure. Really interesting molecule. By interesting, I mean incredibly frustrating. We fight against it all the time. When you expose it to heat, it can form all kinds of different molecules. Here's just a few of these intermediate products that might be formed. Usually with these things, usually with just about anything, if you heat it hot enough for long enough, it's going to end up as CO2, CO, and water vapor, and maybe the phosphorus will go somewhere. But we want to look at all stages of this. And really what we need is good chemical kinetics models to be able to predict what's going to happen when we expose it to a particular condition. And so some of the scientific experiments we do, this is an experiment done out at Nick Glumac's lab with one of the swept-ECQCL systems. So here's the laser system. It was sitting over here on one table. We sent the beam through a high explosive chamber. This was a fairly small chamber, back to a mirror back behind, reflected it and detected on a detector. So just like that Beer's law diagram that I showed toward the beginning, it's kind of that simple. We have a laser source. We have the thing we're measuring. This is, instead of the gas cell, we have this, and we have a detector, and we tune our laser fast and measure what comes out. So for these experiments, used a small detonator, so sort of 50 milligram-ish high explosives. On top of that, we put some DIMP liquid on top of it, detonated it, and saw what happened. So here's some high-speed imagery. You can see things happen very, very fast for these small scale explosions. We can't track this information with the infrared at the 100 microsecond level, but we still see things are still happening out at this tens of millisecond time scales, and we can capture that. So what we saw in these experiments is, first of all, if we just had that detonator, that 50 milligram detonator, blew it up, essentially all we did was make a nice aerosol vapor cloud of DIMP. It didn't really burn at all. And so we can measure it. Here's the spectrum of DIMP. Here's a reference spectrum. We can see it. Time 0 is when the detonation is, and we can see it just sticks around for a long time. Not the situation we want, but it's a good baseline. So what we did next was add aluminum powder to this, and aluminum is commonly used in high explosives to sort of enhance burning, increase the combustion temperatures, make it more of a fireball situation. And that's exactly what it did in this case. So now you can see our DIMP goes away very, very fast. We can see barely a portion of it right here, resembling the spectrum. And what happens is very quickly we form these products we're looking at here is ethene. Here, this peak right here in our measured spectrum is ethene, as well as these ones. And then we see propene as well. And so what's happening is our DIMP molecule down here, we're breaking these bonds right here and here, forming first propene, and then if we continue to react that, we can form ethene. And this, because it's a relatively small detonation, it sort of ends up here. It doesn't go to completion to the CO and CO2, but it gets sort of partially decomposed here. And so this is useful information. High explosives are messy, fun to do, but a little hard to get reproducible scientific information out of it. So another thing we do is more controlled experiments, and here's one of them. So it's looking at the decomposition of this DIMP molecule in controlled hydrogen-oxygen flames. So here's a picture of a spherical combustion chamber that Nick Glumac built out at UIUC. It gets closed up, filled with mixtures of hydrogen, oxygen, and DIMP vapor. And then you can see these two little electrodes right here cause a spark. When that happens, a flame is generated in the center and it propagates out with this nice spherical symmetry. We send our laser through. Here I'm going to add in two lasers, because why use one laser when you can use two? Overlap them in here, detect them with two separate detectors. So here now we can track what's happening in the midwave and the long wave at the same time on the same event. Look, we can change the initial conditions in this, the ratios of hydrogen, oxygen, nitrogen, and DIMP. And what we could do is sort of tailor the conditions to be oxygen-rich versus oxygen-poor conditions, and also change the speed that flame propagates out, the temperatures of those flames. So a lot that can be done. Here's a photo of some of the systems set up out at UIUC. So I mentioned earlier that I work with modelers at Craft Tech. They do these computational fluid dynamics models where they can simulate what will happen as this flame front propagates. So this is as a function of time, it is a function of radius out. We go out the chamber, predict things like what's the peak temperature, what's the DIMP concentration, and then all of the other end combustion products. The spherical combustion chamber was not our idea, it was their idea. I say, wouldn't it be great if you could have a spherical chamber? That would make our lives so much easier. And if you're not thinking of a spherical cow right now, you should be. So in terms of what we measure, does no one know the spherical cow jokes? Am I too old? You know the spherical cow joke. Okay. All right, talk to me afterwards. So here's what we measure for these experiments with this spherical combustion chamber. So initially, we can see in the long wave, this dark line is our initial DIMP spectrum that we're measuring. We ignite it, and rapidly on sort of the tens of millisecond scale, we can see our DIMP concentration, our DIMP spectrum go down. At the same time, we see all this other structure in here. It looks like noise. Some of it is noise, but a lot of this is water vapor features at high temperature that we can measure here. And so here for these conditions we're looking at, within about 20 milliseconds, the DIMP is completely gone. What happens in the midwave is something different. We start with essentially no absorption initially, and after we ignite, we see the appearance of all of these spectral lines, which are due to a combination of water vapor, carbon monoxide, and carbon dioxide. So I skipped over this before, and I'm going to come back to it and spend just a little bit of time right now. I'm showing you a lot of spectra, and what I'm not telling you is how much time and effort goes into interpreting those spectra and analyzing those spectra. So I'll touch on it just briefly in this slide. So here's an example of one of our measured spectra in the midwave infrared up here. There's thousands, if not tens or hundreds of thousands of spectral lines in there overlapping. We can see some of them, but there's a lot there that we can't see that are all overlapping. We can actually get a really good handle on this spectrum and simulate it using spectral databases. So at low temperature, we use a database called HITRAN that usually is used for atmospheric propagation modeling. For combustion systems, we use HITEMP, similar but goes up to higher temperatures relevant for combustion. So these molecules have so many vibrational rotational modes, and as the temperature goes up higher and higher, more of those energy levels get populated. We have more and more transitions, and that's what we're seeing here. Here's our modeled spectrum down below. And we can see not only do we get, a lot of these line positions are matching very well. We're getting the fine structure in there as well. And when we break that down in the individual components, we can see our component from water vapor up here. Here's our CO2 spectrum, and here's our CO spectrum down here. And so we can build up our measured spectrum by combinations of these individual species at the right temperatures. And that's how we're extracting out quantitative information from the spectra. I don't know if it looks easy here or not. It's not easy. We spent a lot of time working on this. But when we do it right, we get really nice quantitative information out. spectroscopically. So I'll just show a few examples from these results. So in the long wave, here's what our DIMP column density does. It starts high, in this case, about 1 times 10 to the 18th per centimeter squared. So those are column density units. It's a concentration, a number density times a path length. And once it's ignited, we can see it drops within sort of these tens of millisecond scales. The speed that it drops depends on the test condition and the flame speed as it propagates out. And we varied that for these 4 test cases I'm showing here. At the same time that our DIMP drops, we see our CO go up and our CO2 go up as well. We can also measure temperatures for all of these species. I won't dwell too much on this. One really interesting thing we found, though, was that the carbon monoxide, when we have oxygen poor conditions, we get more carbon monoxide. We expect that, right? There's not enough oxygen to fully drive that equilibrium all the way to CO2, so we have some CO left over. But even in the oxygen-rich conditions, what we found is that we still get a little bit of CO for a little while, a few tens of milliseconds, and then it continues to react away. So if we didn't have a time-resolved measurement, we would never know that this was happening. And in fact, this wasn't really even included in the model that they ran. They just had the CO going up and staying where it was. So by having this high-speed measurement, we can actually track these highly transient events and learn more about the actual chemical kinetics that are going on. So the other cool thing I want to mention about this is that all of these units here are absolute units. We're counting numbers of molecules or densities of molecules. And if we look at our equation of decomposition, we have our DIMP over here, and going all the way to the other side, full combustion, we have mostly CO and CO2. Every DIMP molecule has 7 carbons. And so if we look up here, we start with 1 unit on this scale. That should contribute 7 carbons. If we add up our carbon monoxide and our carbon dioxide, we get a number pretty close to 7. And so that is it's remarkable to me that we do this measurement, we do a good quality measurement, we do our spectroscopy right, do the spectral fits, we fit the spectrum well, and we can get out these quantitative numbers that make a lot of sense and get pretty close to what we would expect. So that's really one of the powers of quantitative spectroscopy, especially in the infrared. So we've also done higher quantities of explosions. So Nick has other facilities. Here's a larger chamber that can handle up to gram level high explosives. So before all those other measurements, we're allowed to be in the room sitting right next to it. It's still loud, like a loud firecracker in there. It'll make you jump. This one's really loud. We have to be in the next room behind a big concrete wall, and it still kind of shakes the room. And you get used to it after a while. So yeah, looking at a wide range of high explosives and the gases that come off of this. These particular experiments, we weren't looking at the chemical warfare degradation, destruction. We're more looking at the HE properties themselves. One thing we found is that we could detect trace levels of nitrous oxide and in our end products, and a transient ammonia that was formed and then react away. And again, these are things that weren't necessarily predicted by the models that were being developed, but using these high-speed time-resolved techniques with this high spectral resolution and being able to see all these different chemicals, we can pick out these trace species. So I'll move on to the next application, and that's looking at methane flares. So the motivation here, and you may have heard about this in the news recently, it's been a topic that's been covered more and more frequently. We know that methane is a potent greenhouse gas, and what's been found is that it's actually much worse than CO2. It's got about 30 times the global warming potential, every molecule of methane as CO2. We also know the oil and gas industry is a large source of greenhouse gas emissions. We've typically thought that one of the biggest sources was leaks. So, methane extraction facilities, natural gas facilities, they leak. They know that there's waste that's emitted, and that's just emitting pure methane into the air. And that's a big source of methane. A lot of really smart people are working on that problem. However, there's another potential source of methane emission, and that's associated with a process called gas flaring. So gas flaring is the process of burning unwanted methane during oil extraction. So it's not looking specifically for natural gas, it's looking for oil extraction. And in many cases, this natural gas is unfortunately a waste product.
The same.
Excellent callback, thank you, they are. Yes, and I haven't tackled that problem specifically, but I'd love to. Wow, that really threw me off. Thank you. That was great. That was great. So anyways, during oil extraction, we would love to be able to capture all the natural gas that comes along with the liquid oil. Unfortunately, it's not always done. There can be good reasons for that. Safety, so they need pressure regulation, fire suppression. They don't want it to build up so much that there's an explosion potential. I call that a good reason. Economic reasons, they may just be too expensive to transport the natural gas along with the oil. Maybe the economy of that will change in time. This one just floors me. That sometimes there's regulatory barriers where a company is licensed to extract oil, but not natural gas. So they have to burn the gas because they're not allowed to keep it. Anyways, if we accept the fact that there will be methane flaring, it will be burned in the atmosphere, we're still coming out ahead because if we can convert that methane to CO2, it's got a lower global warming potential. So that's really the goal here, is converting this methane to a lower greenhouse gas potential gas of CO2. However, when they do this, it's very important to get high efficiency in this, because in 2023 anyways, 150 billion cubic meters of gas were flared. That's a huge number. Fractions of percent of efficiencies lead to, in this 30 times global warming potential, those are big numbers. So efficiency is very important. So the common industry assumption until very recently was that these flares are always on and running at 98%, what they call destruction and removal efficiency. That's just the percentage of methane that's converted to CO2 or other products. What was found recently, here's one article from 2022 in Science, is that the real world efficiency is oftentimes much, much lower. These flares can go out. When it extinguishes, it's emitting pure methane into the environment, and the DRE is not 98%, it's 0 until it's relit. There can also be conditions of high winds that can reduce the efficiency that weren't accounted for in the models. Impurities in the input gases, all these things can affect the combustion efficiency and ultimately this DRE value. We can also get other incomplete combustion products, soot, CO, sulfur, nitrogen compounds that may be viewed as pollutants. So there are needs in research in this area. We need improved models, always improved models with combustion, and improved measurements of operating flares as the conditions change. So we can't just have a sort of ideal flare, we need to perturb it. So here's some models that Kraftec ran, putting a strong crosswind and looking at what happens. You can see the flame bend over, but we can also look at what happens to the combustion efficiency under those conditions. Oops. So what we set out to do was build and measure a lab scale methane gas flare. There's some photos right here. And then develop the laser diagnostics to measure this sort of in situ, so send our lasers through the flame and measure what's actually happening. Measure as many of these species as possible, so we want to see the methane, CO, CO2, and water vapor are the main combustion relevant gases here. And then ultimately develop models and eventually long-term scale this up to measurements on actual industrial operating flares. So I'll come back to that. For now, on the small scale flares, I've already told you about the ECQCLs, the same one we used for explosives and DIMP we can use to measure CO, CO2, and water vapor. This one won't capture methane. We can do methane in the long wave infrared, but there's a lot of water vapor interference. It turns out to be not quite so optimal. So we ended up using a tunable diode laser. So I spent the first part of the talk saying how bad tunable diode, well, said they were good. They have their place. They do have their place, and here was one of them. Because we're measuring a high methane concentration, we really only cared about one line of methane was enough to detect it. We could measure that one line and do it really well and really fast. What surprised me here was we were actually able to get a temperature measurement out of this by looking at changes in the line width as the temperature goes up. This was somewhat surprising to me. It's not something that's regularly done. I don't know if we just got lucky or we've come up with something that we need to pursue further. But it worked well. So we took our two laser systems. We have our mid-wave ECQCL here. We combined it with our near-infrared DFB laser for methane, combined them into a single beam, sent it, combined it here, sent it through our flare, reflected back behind, and then separated the wavelengths out and detected them. Here's a photo of the breadboard. Again, out at UIUC again. I go there a lot. What they did out there was, so Nick, in working with the Craft Tech team, sort of designed this lab scale methane flare that was a scaled down version of an industrial flare design. So just sort of scale everything down to closely mimic the operating conditions as possible. What it comes down to is it's got a central region right here that the methane comes out, air comes out the outside, and both those can be varied independently. And this is how they actually operate the flares in the field. And having this so-called co-flow of air that can be adjusted can help you compensate for the effect of crosswinds to some extent. These are, for those who know combustion, it's a non-premixed flame, meaning the fuel and the oxidizers are not mixed before combustion, and so that leads to more interesting dynamics and more variable flames. So showed this before. So we talk about this as being a scaled down large burner. It's also a scaled up Bunsen burner, basically. For scale, this is about 1 meter high at times as it's going. It's a lot of fun to be around. So here's our setup at UIUC. Our instruments were located outside. He had sort of a large indoor chamber with big, thick concrete walls. Yes, he uses this for explosive measurements too. We just used it for these methane experiments. It was nice. It had ventilation at the top, nice controlled space to do this. So our lasers and detectors were out here. We had a mirror on the other side. We sent our beam through the flare and back and changed the conditions of that operating flare. Here's a photo sort of outside that room. It was a little bit awkward setting up the experiment up on this high platform above my head. I had to climb up on the table and be careful not to drop anything. And essentially here's sort of standing up, looking at the beam path. We can see going through the room, and you can see the flare there. Didn't go as well as I wanted. There we go. So now you can see sort of looking straight through along the beams and coming back through that flare. So one problem we have is we'd really like to be able to measure how things change as a function of height up this flare. And it's about 1 meter tall, so that's a pretty big distance. We can think of ways that we could come up with some fancy beam steering optics, periscopes, motorized stages, maybe some galvos to probe that, and that'd be really cool. But we have graduate students, and they can take this hydraulic lift and slowly lower it down while we're measuring through here. And we actually got everything we needed that way. It was great. I felt really bad for Caitlin, though, because we did this about 30 or 40 times over a couple days. And I think her legs were hurting after the end of that from pushing on this hydraulic thing. But it was great. It worked out well. I'll also point out that, so we used sort of video images of every run. We watched it as it fell down using a very, very high-tech measurement device of a ballpoint pen and a ruler. And we could track this as it went down and then correlate height to position or time. It doesn't have to be a high-tech solution. When you're out somewhere without a full lab available or a hardware store within driving range, you make do with what you have. And it worked just fine for what we needed. So when we operate these systems, I haven't shown something like this before, and I think it's useful to see. So there's 2 computers here, screens. This is the software we're using to control these lasers. So this is our methane DFB laser, the narrow tuning laser over here. If you look closely, you'll be able to see a single absorption line there. It's going down because it's transmission. Here is our ECQCL over here. We see our outgoing and return beams up here. And then here's a normalized spectrum down here. That's going to be the absorbance spectrum. And here's what it looks like when they operate. And so this really highlights what we're doing here. So you can see these are dancing around a lot. We're going through a turbulent flame. So the power is sort of wandering all over the place. The beam's moving, breaking up. We're getting scintillation effects. A lot of essentially what we would consider turbulence noise. But because we're scanning fast, we've completed our scan before it's changed very much. So what we see is this sort of baseline offset. It's just pretty flat and it's going up and down. And what that means is when we do our fitting, that doesn't look like any spectral feature we're looking for. So we can just fit it out of our spectrum, and it really doesn't interfere with our spectrum recovery method. So that's really the benefits of scanning fast through these turbulent conditions. So I won't go through certainly all of the results we got. I made a lot of measurements as we did height profiles through the flares. So here's our methane. Methane goes down as we go up the flare. Temperature goes up. We can measure CO, CO2, water vapor, measure temperatures for all those. Interesting thing happens when we turn up the air co-flow rate. We can get conditions where the flame lifts off or detached. See a little clip right there. So there's this gap where we have unburned methane here. We have to reach a certain height level before it will combust. And then the conditions change. You can see you get a bluer flame in this case. Our CO, CO2, water vapor profiles change. Lots of things change. At the end of the day, kind of what we found is that as we turn our co-flow air rate up too high, we start to get lower and lower combustion efficiency as we get more turbulent mixing and sort of pockets of methane that can escape the region before they have time to burn. And so as we turn up our air flow rate, our destruction removal efficiency and combustion efficiency go down. What I'm not showing here is that we could turn it up high enough that it would extinguish the flame completely, of course, dropping all the way down to 0 for both those numbers. Just briefly I mentioned this at the beginning. We can do the same sorts of experiments on more complicated flames like biomass burning. This was interesting because we could see, in addition to the combustion gases, the CO, CO2 water vapor, we could also see other pyrolysis-related gases, ammonia, ethene, ethylene, methanol coming off of this. And this is from pyrolysis processes. Before the flame reaches the burn material, it heats it up and forms all of these partial combustion products. So our real concept for these methane flare diagnostics is that we would take our laser system, put it in the back of a van or some other vehicle, go out to these flaring sites, send a beam up to a drone back behind with a reflector on it, reflect back in, and basically do that same experiment but on a much larger scale outdoors in a standoff remote sensing method. So as of now, that probably sounds like a big stretch based on what I've shown you with these laboratory scale experiments. And so that's why I wanted to spend a little time at the end talking about some of the remote sensing experiments that give us confidence that that sort of an approach would work using these lasers. So talked about at the beginning, remote chemical plume detection, or really any source out in the atmosphere. We'd like to be able to measure things from far away, if it's a hazardous material or if it's an explosive where we absolutely have to be far away. So the concept is this: we take our laser system and we just maybe expand the beam, send it out over a much longer path to some sort of a mirror or retroreflector, reflect it back, and now we can detect everything along this path. If it's just the atmosphere, we can detect everything in the atmosphere. If we have something like a gas plume or a methane flare in between, we can measure that in addition to the atmosphere along that path. So some of our first remote sensing measurements were actually done here in this very building, or more specifically on top of this building. So we took one of our laser systems up to the top of Manel. You can see we even got an appearance from the dean, which is really fun. And there's Jason. What was this, 5 years ago or so? We'll say. Okay. So we set up on the rooftop here, set up a reflector. You can see it on a tripod right there over on, I think it was the Stewart building at the time? Yeah, okay. Sent the beam out 235 meters one way. So about 460, 470 both ways. And then set the laser running and released a bunch of different gas chemicals in the beam path and looked at their time dependence. This was more of a proof of concept study to show that we can do it and that we can measure things very fast and distinguish all of these different chemicals. So later on, we extended this out, so we don't need to stop at 200 meters. We went out to Socorro, the Energetic Materials Research and Testing Center, EMERTEC, out in Socorro. There we extended the range out to 1.5 kilometers one way. And this is getting to be a decent distance, especially for an active instrument like this. So our instruments were up here on the hill. We sent them down to a retroreflector, 1.5 kilometers away, reflected back. For these measurements, we had a passive hyperspectral imager as well. So this is one of those broadband incoherent instruments I mentioned at the beginning. And what we wanted to do was put them both looking at the same scene and compare the results and see what can we learn by combining these two methods at the same time. And so we did a lot of different plume releases out there, primarily looking at sulfur hexafluoride and a different type of freon gas as well. So I showed this movie at the beginning. So this was taken with that Telops hyperspectral imager. It's really looking at thermal contrast between the scene, you can kind of see in grayscale back here, and plumes that enter that. Really nice results in terms of getting a spatial map of what that plume's doing, but it's pretty slow. It's a few seconds for each of these frames. We don't get very good spectral resolution. It's sensitive enough to see the SF6, but it wasn't sensitive enough to see the Freon that was released here too. So what we did was we looked at the part of that image where our retroreflector was sitting. So we're sending our QCO beam along this line to a reflector here. So we're really looking at this one region in the image with our laser-based instrument. And we can look as a function of time what's happening at that space. So in our hyperspectral imager, we get this signal. It's uncalibrated, but it's relative SF6 intensity. That's what we see here. And it matched pretty well with the time that it was released from this location up here. Looking at the QCL system, we can see as a function of time, very good correlation in time between those signals. We get a faster response, we get higher sensitivity, we can see other chemicals as well, but the correlation is very good. We actually used our QCL instrument to calibrate the TELOPS hyperspectral imager, which very, very hard to calibrate these systems in the field. That's one of the problems that they face. And so we figured out how to use the QCL measurement as a calibration source for that instrument and get quantitative data out of it. Getting close to the end here, I just have a few more slides. In terms of sensitivity for these techniques, they can be very sensitive. We typically, the numbers I like to quote for most chemicals is about 0.1 to 1 part per million times a meter in sensitivity. So what that means is if I have a plume that's 1 meter in size, we could see a gas at a 1 part per million concentration. So 1 molecule for every million molecules of air. If we look over that entire path, sort of distributed, and look at atmospheric chemicals, because we have such a long path length, we can essentially divide this by a very large number. We can get down to sort of the tens of part per trillion sensitivity levels. And so now we can start thinking about looking at background levels of trace gases like these freons, SF6, that we wouldn't normally be able to detect, especially with an active laser-based method. But what's really important here, there's other methods that can get these levels of sensitivity, but it takes a long time to get there. It has to average for a very long time to drive the noise down and get that. The benefit of this tunable laser technology, whether it's an ECQCL or a tunable diode laser, is you can get the sensitivity at very high speeds. So you get it fast. When we look at averaging properties, we get high sensitivity at, even at a millisecond, we're close to a part per million meter for SF6. And so for things like transient plumes, combustion, things that don't last very long, we need that high sensitivity very fast because the source is just gone before we have a chance to average it. So as a final example of that, we were able to take one of these systems out to the Lawrence Livermore National Laboratory, their Site 300 high explosives area, where they were detonating high explosives. They did a 41 kilogram explosion. We're talking about milligrams and grams before. Now we're up to kilograms of this high explosive LX14. We were 830 meters away. Even at that distance, up on this sort of observation tower inside, we could feel the shock wave as it came by and hit. It was quite dramatic. You can see the fireball here from one photograph, and when this fireball went off, it generated, I'm just going through laser pointers left and right. This one's almost going too. It generates this gas plume. We're able to detect the gases in it, mostly CO, CO2. But again, we were able to see the nitrous oxide as well, which was something that wasn't necessarily expected. So we've continued to improve the system. I showed you some early prototypes where it's sort of built on this extrusion frame. All the optics are out, not really suitable for any long-term deployment. We needed to be there. Let's keep advancing. So our latest system has been, better packaged. There's a cover off here. You can see the cover inside. Different telescope design. It's basically a modified Newtonian telescope. Larger aperture. This is going to let us get longer distances. We think with this design, we're predicting we can extend out our range to 5 to 10 kilometers. We'll hopefully be setting up these measurements, maybe again on the roof here. If we do, maybe we can send out a notice and people can come by and take a look at it in action. Other improvements, we have motorized stages, so now we can remotely control the pointing and the elevation of this system. We recently deployed this system at a even larger underground explosion. I can't talk about it yet. I can mention it, I just can't give any results on it. You can look up in the news information on large underground explosive tests at the Nevada National Security Site, and you will uncover things. We're not talking about kilograms, we're talking about tons of high explosives underground. And we had our system set up above ground to monitor gases that essentially come from underground up to the surface. So that's where we're going with this. So to sum up, I've showed you a lot of different examples of using tunable laser spectroscopy in the infrared for chemical sensing, specifically in these extreme environments, plumes, atmospheric plumes, flames, high explosive detonations. As long as we can scan faster than the timescales of the signal to noise, it really doesn't bother us too much. We can fit that out in our analysis. If we do our analysis right, we can get quantitative information out. We get the high sensitivity at a high speed, which is important for transient events. And so we can get out this sort of combination of broad tuning ranges, fast rates, high resolution, gets us the chemical and physical information we need. And I talked about a few different applications. Always looking for new applications, continuing to develop the technology further, make it more and more easier to use, more commercial ready. Hopefully, eventually get this commercialized and get it into other people's hands. I do like traveling around the country, but I can only do so much. We need other people out there using these systems. Lots of other application areas this can be applied to, whether it's atmospheric monitoring. There's a lot of nuclear process monitoring applications. This is where the isotopes comes back, because we can measure different molecular isotopes. That can be very useful for a lot of nuclear processes and reactors. Agriculture applications, so whether it's food storage, feedlot emissions, spherical cow emissions, there you go, that's in there. Microplastic detections. I didn't talk about the using this in the lab for a hyperspectral infrared microscopy application. So sort of the opposite extreme from the standoff. We can look at very small systems and do fast, high-speed infrared imaging at a microscopic level. And then other applications as well. Always looking for collaboration opportunities. So if you think of things that are interesting, want to collaborate, let me know. Love to talk about applications for this technology. So thank you very much for your attention. Happy to answer any questions that people might have.
Great, thanks, Mark. Yeah, we'll open up any questions.
When you're given the weights of the explosives you're measuring, is that a gross weight or net explosive weight?
Oh, that's a good question. That's a question that Nick should answer. I believe that's I'm not even going to answer. No, I would probably get it wrong. Those are the numbers that he told me. So on a lot of these, you're talking about the small explosives, right?
Yeah.
Yeah, so some of them are just sort of standard detonators. So RP2 detonators, other types of detonators, we could look up the specs on those pretty easily. The other ones that are the detonator combined with a massive HE, he makes those himself in his lab, and so I'm not sure on the exact details of how that's done, but those are the masses that he gave me. If you really wanted to know, we could find out.
Very interesting talk. One question, you probably thought about deflection or backscattering also. Would that ever work?
Yes, so that's an excellent question. So we've done backscatter from sort of metal plates. We actually did some of those here at the rooftop measurement. We put a flat aluminum plate and was able to get enough reflected light off of that came back that we were able to detect even at 230 meters. One property of the infrared, because of the long wavelength, scattering from surfaces is more directional. It's less isotropic. So you don't get sort of the same speckle patterns that you get, say, with visible light. It's more directional. So that's good and bad. If your angle is just right, you can get a very, very strong glint in the infrared and get really, really strong signals, even from surfaces that may look rough. The problem is, if you're off that angle even slightly, you don't have enough isotropic emission oftentimes to detect. So there's challenges with that. I think the rough surfaces, infrared rough, at short ranges is definitely possible. People have looked at that and demonstrated that. Longer ranges, glint mode, as I call it, so sort of topographic target, if it's at the right angle, yes, we can get pretty good reflections back from those.
Just following up on Rolf's question.
Yeah.
I think up at 10 microns, you start to gain with heterodyne detection methods
Hmm.
or homodyne detection methods. I wonder if that would be a way to increase that sensitivity for that backscatter light that would be very low.
That's-
Has anyone tried that?
Yes, actually, they have. Yeah, there's a group out in UK who demonstrated that. A really, really nice technique for doing that. Yeah.
Did you say methane spectrum gets narrower with increasing temperature?
Haha, yes.
Why?
This is fun. So this is one that I use to test graduate students all the time. And I tell them to ask their professors, and they can stump their professors too. So it comes about because the dominant part of the line width at these temperatures and pressures is van der Waals pressure broadening. And what happens is as the temperature increases, so it's collisional broadening with other air molecules or methane. And what happens is as the temperature goes up, the van der Waals line width actually goes down. And it goes down faster than the Doppler broadening goes up. You can calculate this out, actually. It has to do with the line width determined by the frequency of collisions. And at constant pressure, as you sort of expand your gas out, the collision frequency ends up going down, even though your speed is going up from the temperature, the density goes down more. And so the net line width gets narrower as the temperature goes up. It's not a strong effect. You have to go over sort of the hundreds to thousands of Kelvin regime to see these effects well, but for combustion, we are at those temperatures, so it works. I'm so glad you asked that question. That's a great question.
Another question there.
So there was an image we were showing that there was some spatial resolution. Is that some kind of beam scanning, or how do we get spatial resolution?
It's spatial resolution.
So
on the
there was
methane,
like- sorry, where you were showing that gas plume sort of moving over the valley.
oh yeah, so that was taken with the TELOPS hyperspectral emitter. So for the, I should have described a little bit more about what a TELOPS is. So it's an FTIR instrument combined with an infrared camera. They're extremely expensive high-tech devices, but it gets you a full scene of infrared spectrally resolved light. And so you can do chemical identification. Essentially, every pixel in your image has an infrared spectrum associated with it. Yeah, so that was where the imaging came from. We were only looking at one line of sight in there. But the cool thing was that we could use the information we got from that one pixel and extend it to all of the other pixels and calibrate the whole image based on that one pixel that we measured at higher fidelity and quantitative results.
Just wanted to, when you're talking about the tunable and laser, based on my understanding, one of the difficulty is like most hopping for the range of them and you talking about long tunability range. And I just wondered how you control this most hopping.
Yes, another excellent question. I didn't have time to get into details on that. So I made the ECQCL sound kind of simple and trivial, but you're right. There are mode hops to worry about. There's a lot of sort of, tricks and clever things we do to not remove them completely. They're still there. But we do special things with the current modulation to sort of smear them out. And we do synchronous lock-in detection, which also helps smear them out. And all of these techniques give us these really nice, smooth spectra. For these sort of line widths that we're looking at atmospheric gases, and the line widths are broad enough that the mode hops really don't bother us at that level. If we were looking at a low pressure gas cell, we would definitely see the mode hops, and we wouldn't be able to measure those well. We have other techniques with the same laser to do a mode hop free scan, but only over smaller ranges. So it'd be similar to a tunable diode laser. The advantage though is that we can pick that tuning range from anywhere within our broad gain bandwidth. So we essentially would have a bank of 100 or 200 tunable diode lasers all in one box in that case. Yeah, great question, thank you.
Have you ever, from exposing a substance to the laser, has that ever caused combustion or detonation?
Well, I want to admit having burned myself in the lab once. I think I just did. Yeah, they can be powerful enough. These systems as constructed, they're actually very low power, usually 5 or 10 milliwatts average power at most. We expand the beam out, for the remote sensing, we expand the beam out to be a large enough size that it's completely eye safe, which is great. We don't have to worry about eye safety, which is for remote sensing with lasers, that's usually a big concern and really limits where you can deploy these systems. Out in the infrared with the low power, large beams, we can still do the long range measurements, which is great, but we don't have to worry about eye safety. It's more of a skin burn hazard than anything, not at these power levels. But there are systems that will, other QCLs that will generate, watt level output powers, CW, very strong, very spectrally bright sources. One application that people have looked at for these type of quantum cascade lasers is infrared countermeasure. So blinding missiles, heat-seeking missiles with a very bright laser source. So yes, they've worked on high power sources, not these ones specifically, but definitely possible.
Right, we have one question from Zoom here. How can broadband supercontinuum fiber lasers contribute? We also have high average powers, tens of watts, high spatial coherence, and can also cover broad spectral region from 1 to 5 microns.
Yeah, so they definitely have a place. So I haven't talked about all of the infrared sources that are out there. There's other sources. There's frequency comb sources as well. They can get out to these ranges. Either you can have a QCL based frequency comb directly emitting. Work's been done on that. You can have difference frequency mixing based comb sources that sort of step out into the infrared. And then the supercontinuum type sources as well. They all have trade-offs. They all have their place. A lot of times with the broadband source, even if it's a bright laser source, you still need a good way to do the spectral resolution. So if it's not a tunable laser, you have to figure out how to extract that spectrum out. So with some sources, you might be left with a spectrometer again. You're sort of limited. Yes, you have a bright source. You've overcome that part of the FTIR problem, but you still may have a spectral resolution. With the frequency combs, there's dual comb spectroscopy, which is a great way to get that spectral resolution. Very powerful. I think there's different trade-offs with signal to noise and averaging times with these different techniques. I like to say that they all have their place depending on the application. This one's niche, I think, is these very fast events where you really need the high sensitivity at high speeds to be able to measure them at all. Hope that answered the question.
I think so.
Okay. You don't.
Yeah, any other questions? Well, if not, one more, John.
You mentioned that destruction efficiency of methane decreasing the co-flow of air, but that was also kind of necessary for crosswinds. Do you know, does that same trend kind of hold true? Do you have a crosswind or?
Yeah, I didn't show those results. So we did have results looking at varying the crosswind. And so, yeah, so it's sort of when there's a crosswind, you need the co-flow initially to stabilize a little bit better the flame. But then again, there's another point where it gets too strong and you sort of get this runaway condition again and you lose your DRE again. Yeah, good question. We really just scratched the surface on what we could do with that. There's so much more we could do looking at those methane flares and characterizing them. Maybe we'll get a motorized lift next time so Caitlin doesn't have to kill her legs.
Hey, great. Well, Mark is around, so if you have any other follow-up questions, find it right here in Optical Sciences. Let's thank him one more time.